Hello everybody. Today we're going to try to build a confidence interval from scratch. What I mean by that is if we collect data, actual data, from there, could we build a confidence interval? The answer is of course. Let's check that out. So here we have this data set. What we have is in the left column the day of the month, and number two, the second column, the count, would be the number of patients per day at the local clinic. The question is, are the number of patients at the clinic normally distributed? And if they are, then can I predict, can I build a confidence interval, whether it's 90, 95, or 99? I want to do all three. Can I build the 90, 95%, and 99% confidence interval for the true average number of patients per day at this local clinic? Why would I care about that? For staffing purposes. Do I have enough staff on hand to handle the patient load per day? So first, in order to build a confidence interval, let's go to our confidence interval formula. You need to decide which one it's going to be. We have two confidence intervals for the mean, two confidence intervals for the average. How do I know I'm picking one of these two? Because again, I have a single stream of data. In that single stream, I care about the average number of patients per day. That's an average number of patients per day. That means I care about one of these two. The question is which one? Well, because all I have is sample data, it's this one. When I have S, sample data, I have to build this confidence interval, which means I need X bar, S, N, and T. These are the four letters I need to build my confidence interval. So that's the first step. I have my steps for building a confidence interval. And my first step is always picking the right formula. Now, to pick the right formula, I also have to know something about the whole situation. That is X bar, N. Do I want S or sigma? In this case, I only got S. I do not have the population standard deviation for clinic time. I don't have that. And of course, I also need the T value. With these four values, I can create the margin of error, and from that, I can create the lower bound and the upper bound. And I can do this for whatever confidence interval you want, 90%, 95%, 99%. All I need is some information, X bar, N, and S. Well, what are each one of these components? X bar is the sample average, so I need the average of my sample. I need N. How many days did I sample for? And I need the spread of the sample. So how do I find each of these? Well, in Excel, the easiest way to determine X bar, N, and S is via the descriptive box. But, well, not but, let's do that. Let's build the descriptive box. So the first thing, whenever I'm given data, and I should back up, my grand poobah thing is to build the confidence intervals, okay? But I got to back up. Whenever somebody gives me data, the first thing I want to do is go to data, go to data analysis. If you do not have this, pause the video and ask Google how to add the data analysis icon for Excel. That needs to be here. The good news is once you put it on and enable it, it always is here. All right, welcome back to the video. Now you should have data analysis button. So I click on data analysis, descriptive statistics. So I'm going to take you through what I would do in true research. First thing I would do is get some descriptive statistics out of my data. How do I do that? Well, read the rules. Input. What is your data? Now here's my data. Click. Is it grouped by columns? Of course. Do you have labels? I do, but I didn't highlight it. That's why I'm not checking this. I didn't highlight the label. If you did, you would check there. Notice I only have one column of data. This is just kind of a counter for me. Which day the patients were on, blah, blah, blah. This is the actual data. How many patients I had on a particular day. This is the data I'm actually caring about. All right. You have to click Summary Statistics or it won't summarize for you. Output range. That's up to you. I like to put it on the same sheet, but wherever you put it, wherever you place it, make sure bottom and to the right is pretty empty. All right. You need a nice little grid to drop in your data dump. All right. That's it. Click OK. Boom. And we get our descriptive statistics here. We get our descriptive statistics. on our patients. So what do I see in here? First of all, I notice I have 30 values. Got it. I have 30 values. Done. Because that's what it is. I have 30 days. The great thing about 30 days is because of the central limit theorem, I really don't have to check anything more about normality because of the central limit theorem, I know that I have roughly normal distribution for the sample. Now, I have no clue about the clinic, okay? I truly have no clue about the patients in the clinic. But I do know that samples of average 30 are roughly normal. And that's the key. Sampling average, which I'm studying, is roughly 30. Is roughly normal because N, which is 30, is the threshold for the central limit theorem. Now, what else do I know? Well, I know the standard deviation. Look below in the chart. And in fact, I'm just going to use the nice number. The standard deviation out to many decimals is right there. Boom. The sample average, I got that too. The sample average is right there. The mean, got that to many decimals. And that's really cool. So I have the X bar, the S, all lined up nicely for the 90% confidence interval. In fact, same numbers I need for the 95 and 99. So knowing these three means all this is all filled in. So really, I need to find the t-value. I'm going to find that later. What I'm curious about is, because this is kind of like a different question, what are the attributes of this distribution? Well, let's investigate a little bit. Well, we have the mean and median. And if the mean and median are relatively close, then we have a relatively symmetric picture. That is a symmetric box plot or histogram if I built them. If I built the histogram and box plot, I'd see roughly symmetry because the mean would be close to the median if there's no outliers to pull it away. And so since they're really close, that's kind of like my first check for normality. If the mean and median are really close, then I have what I call my first quick check for normality. Second thing, the skewness. You can look it up in Excel, how they build the skewness formula. But bottom line, the skewness talks to you about the tail, which direction the tail goes. If the skewness is perfectly zero, then what we have is a pure symmetric curve. And think about it, a normal picture is symmetric. A normal picture, you can cut it in half and bend it in half and it looks proportional. The skewness is slightly positive. I mean very slightly positive. 0.07 is very slightly positive. My barrier for skewness is usually 1/2 to -1/2. A positive number represents a positive skew. A negative number represents a negative skew. Really, it tells me which way the tails are going. Right now, there's a slight tail to the right-hand side, but it's probably not noticeable. So I would say with check 1 and check 2, I have a pretty normal distribution. But let's check this out. Why don't we draw something? Let's draw the box plot. You know what I mean? We have the ability to insert a picture recommended within seconds. And the picture I care about, the box and whisker plot, is right here. By the way, if you're curious in how fast I'm doing this, go back to my previous videos on box plots, on descriptive box, on checking normality. These are all things I've gone through by this time in our video stream. If you've watched my videos from video 1 to video now, kind of check out my playlist. I got week 1 playlist, week 2 playlist. We are now actually in week 4 playlist, if you're thinking about it. We're 4 weeks into what I call a summer semester of statistics. So box and whiskers. There it is. Click OK. Why am I doing this? Well, the central limit theorem says it's normal. That is the sampling average. So I'm good to go. But I'm just having fun verifying from my information from the previous chapters that I have roughly normal, just for my curious sake. These two are close, the mean and median. The skewness is close to 0. That's another check. Another check. Let me bring out the data by clicking data labels. If the spread from the quartile 3 to the max and quartile 1 to the minimum are pretty close, and they are 3, roughly 3, then that means we have a really nice spread, a pretty uniform spread. So once again, I'm really looking at a uniform / symmetric, and in this case, a very normal distribution. Now, how can I guarantee normality? Well, to guarantee normality, you could do an advanced test. I'm just giving you quick, dirty, basic stats 1 checks. The mean and median are close, the skewness is close to 0, and the box plot looks pretty symmetric. These are all standard checks. You could also build the NPP plot if you'd like to further analyze the normality here. And you can check, again, my video out on checking normality to see that. Right now, I want to get back to the question at hand. I really want to build the t-distribution, and I can. The t-distribution follows the normal model. To build the t-distribution, I need either the central limit theorem to kick in or all of this analysis that I'm doing. That's why I'm doing this analysis, to really, really fundamentally understand that I can use the t-distribution. To me, the t-distribution is a cousin of the normal distribution. They're very similar distributions. All right? So, how do I find it? Well, from my previous videos, you understand you can build a confidence interval using t.inverse. You just got to understand what to put in. You need the probability. What do you mean by the probability? Well, the probability would be the probability below the marker for the middle 90%. Imagine drawing the t-distribution and putting up 2 bars, and in between the 2 bars you have 90%, which means you have 5% on each side. Which means if you look at that upper bar, how much area is below the upper bar? That would be 95%. And so that's why I'm putting in 95%. Degrees of freedom for the t-distribution is n-1. And so that's why I'm plugging this in. Boom, I have my t-distribution value. I have my t value. These 4 values, going back to our formula sheet, are the values I need to build this. At any time, pause the video. Take a picture of my formulas that I've been using. You'll see them throughout all the other videos I build on confidence intervals. By the way, we could have used the T chart, and let's try that just for good time's sake. I know my N is 30, and I know I want the 90% confidence interval. So we go to the T table. So here's a T table I've downloaded. The T table. First, you need your degrees of freedom. Degrees of freedom is n-1. So there it is, n-1. Awesome. If it's not in the table, get a better table or just use Excel or some computer software. Here is your degrees of freedom. The good news, I love this table because it has the confidence already written here. So for the most popular confidence. If the teacher picks an 88% confidence level, then you're going to just have to pick your lucky guess. I don't like guessing. I like to have exact numbers. So again, 29 going to 90% confidence interval. I better have gotten via Excel 1.699. Let's verify that. Well, look at that, 1.699, and I actually have more accuracy here. Cool. All right, margin of error time. Well, the margin of error, by definition, is the t-distribution value times the standard deviation divided by the square root of the sample size. Please refer to my formula sheet on how I did that. I'm pausing, giving you guys a chance to look at the Excel commands. Again, by now in this video, if you've kind of watched my videos in a flow, we're in the 4th week. If you haven't, welcome. Just hold on and go back to previous videos if you need more details. All right. Once I have the margin of error, I can build the lower bound. The lower bound in the confidence intervals is always built from the center, X bar, and X bar is the center of every confidence interval for the mean. X bar is the center. The lower bound is minus the error. The upper bound will be the mean, the center of all confidence intervals, plus the error. And I gotta be careful when I say all confidence intervals. I mean all confidence intervals for average. That's 2 of them that I have on my formula sheet. And there it is. There's your lower bound and upper bound on the number of patients with 90% confidence. With 90% confidence, on average per day, I expect somewhere between 79.27 and 80.39 patients. That is the numbers I expect. Now, given this confidence interval, I can now ask my managers for enough people to have on staff to cover these number of patients, whether you look at the lower bound or the upper bound when you talk about it. I know they're really close here. That's great to know. They're really close because our error is really nice. It's really nice to have a tight error. If this error was large, this interval would be large, and we'd be looking at bigger decisions to make in management. Because this is a tight window, we know we're somewhere between 79 and 81, right? That's not that much difference. That's 2 extra patients. Unless we're trying to be very, very clear on patient care, and that would mean the hiring of a new HR representative, a new check-in person, a new nurse, a new doctor, whatever's needed to cover that extra person, that extra patient. A lot can go into the thought behind the confidence interval once it's built. What's the cool thing is once a confidence interval is built correctly, you can copy and paste and build many confidence intervals fast and quick. So, for example, we have 90%. I can quickly get over to 95% just by utilizing what we've already done. First of all, the average is the average. Got it. Sorry. The average is the average. Got it. That doesn't change. Average is average. Sample size 30. I'm not going to waste time. It's 30. I'm not sure why the equals actually didn't come out. That's kind of funny to me. Equals the mean. Done. The standard deviation, it's the same number all the way across. There it is. So I can quickly write across, write in the standard deviations because they're right there. That's the great thing about Excel, the automation. The t-value, well, t dot inverse. Let's play the game. 95% confidence. How much is from that right bar all the way down to the bottom? I'm looking at the right bar. So imagine the T distribution drawn. Imagine 2 bars built, left and right bar, covering 90%, 95% of the area. How much is outside for each bar? 2.5%. That's why I'm using 0.975 here. Degrees of freedom, same degrees of freedom, 29 because that's n minus 1. Vice versa. One more time, hit me, baby. 0.995. I'll let you think about that. 0.995. Wow, did I know that was 0.995? Again, visualize. Draw the picture if needed. And you'll see it. Margin of error? Well, the great thing is once you have a formula written right, you could just copy the formula across. Once you have a formula written right, wow, you can just copy the formula across and it makes your life easy. That's the great thing. Once you have one of these written right, you can overwrite the numbers and everything changes and you can just get to the cool part, the analyzing. I mean, everything to me is cool. The building of this and the analyzing. So look how quickly I built the 90%, the 95%, and the 99% confidence interval for the true average number of patients. Now, which confidence interval is the one you want? Well, it depends. Does the boss want 90%, 95%, or extremely high confidence, 99%? Notice what happens as you go up in the confidence level. Very important to me. The t-value gets bigger. I can't explain that enough. As the confidence goes up, the t-value gets bigger. If the t-value gets bigger, and that's the multiplier in the margin of error, then the margin of error gets bigger. The error gets bigger as you let in more confidence. You want more confidence, your error has to get bigger. If your error gets bigger, that means your bounds get bigger. And honestly, in this case, the bounds aren't even that bad. You really got to turn to the boss and say, boss, I built you 3 confidence intervals. Which one do you want? You could report all 3 if you like. I'm honestly shocked by how tight this confidence interval is, right? From 78.9 patients per day to 80.7 patients per day. I'm 99% confident that the true average number of patients we're going to see is somewhere between 78.9 and 80.7. That is great news. Very specific. Very helpful, again, when I'm trying to hire the right number of clinicians, doctors, nurses, staff, bottom line. And even if this question is about patient care, you can switch this to customer care and think about lines, queuing. How many bank tellers do I need with 80 roughly customers per day? Building a confidence interval on what's the worst case scenario, the high case scenario. It's very, very important to know how to build these so that we can get to the second level, understanding why they're important to us, how they make forecasts, how they make predictions for us. All right, guys. Thank you for watching this video. Stay tuned for others.